The next set of problems is a problem type called multi-step synthesis. So all of the synthesis that we've done so far has been just one step. You can transform the starting material into the product by doing only one reaction or using only one recipe. And so now we're going to get into a type of synthesis where you can transform one molecule into another, but you can't do it all at once. You'll have to transform it into a few other things before you can finally make the product you want. So these are multi-step syntheses. I'll show you what something like this would look like. It's presented in much the same way as any synthesis question, where they'll give you a reactant, they'll give you a product, and they're just asking, what do you need in order to make this transformation happen? The difference is, though, that we can't do just one thing. We're going to have to do many things. Now, this becomes more and more nonlinear as you progress in organic chemistry. But since this is the first time we're really working on these multi-step synthesis problems together, we're going to do a very structured type of multi-step synthesis problem. And that is that we're going to move a leaving group in this first type from one place in the molecule to another, and you can see that's what's happening here. We have a leaving group in one place, and we're moving it to a very different place on the molecule. And the other thing we're going to do is learn how to move a pi bond from one place in a molecule to another. So these are the last two questions on the test. One will be moving a leaving group from one place to another. One will be moving a pi bond from one place to another. So in the molecule here, the pi bond starts at the bottom and you have it at the top at the end. These are structured types of multi-step synthesis problems because what they ultimately are going to be are a series of alternating elimination and addition reactions. So we're going to do alternating elimination and addition reactions to make these transformations happen. To move the leaving groups, to move the pi bonds, we're going to do alternating elimination and addition reactions. How do you know when to do elimination? You'll do elimination if you have a leaving group. You can't do elimination with just a leaving group. You have to do, you can't do addition with just a leaving group. You have to do elimination. How do you know if you'll do addition? You'll do addition if you have a pi bond. And notice, by doing elimination, you create a pi bond. And by doing addition, you can add a leaving group. So these are the two sort of strategies that we're going to use, the two techniques we're going to use, and they're going to alternate. So first we'll do elimination, then we'll do addition, then elimination, then addition, until we arrive at our product. The last thing we have to review before we dive into one of these problems is how you can control the direction of elimination and addition. So in elimination, you can control the direction by getting either the Zaitsev or the Hofmann product. Right? If you use a skinny base, then like sodium hydroxide, for example, then you can get the Zaitsev product as your major product. If you use a bulky base, like potassium tert-butoxide, for example, then you would get the Hofmann product as your major product. So that's how we can control where a double bond forms when we do an elimination reaction. For addition reactions, you can control where the leaving group is added by using either Markovnikov or anti-Markovnikov addition. And I want to focus on just one reaction. We'll really just be doing one reaction with these multi-step syntheses in this chapter, one addition reaction, and that's hydrohalogenation. That's not because that's the only useful addition reaction. That's far from it. It's not even because it's the only one you could do in these multi-step syntheses. Again, that's very far from it. We're using hydrohalogenation because of the type of multi-step synthesis we're doing. We're either going to move a leaving group, and so you can add that leaving group by doing hydrohalogenation, or we're going to be moving a pi bond. And that means that if we add something and get rid of a pi bond, we'd better add something that can leave. And you can do that in hydrohalogenation. You'll see that play out as we do a couple of these exercises. But the way you would do Markovnikov addition with hydrohalogenation is you just add the HX. And remember, X in organic chemistry is any halogen. So for us, that's going to be chlorine, bromine, or iodine. And the way you can do anti-Markovnikov addition with hydrohalogenation is if you add a peroxide. A peroxide is a molecule that has, now this is not a peroxy acid like you would use in anti-dihydroxylation. A peroxide just has two oxygens single bonded to each other. The simplest peroxide is hydrogen peroxide, H2O2, which you might remember is in the second step of hydroboration oxidation, hydrogen peroxide. The reactive part of this molecule is the single bond between oxygens. Right? What's unique about carbon is that it can form stable single bonds to itself. Other elements can't do that. And so this bond between those oxygens is very reactive, and we'll learn how it reacts in chapter 11. And we'll see why this gives you the anti-Markovnikov product. But it doesn't have to be hydrogens at the end, right? It really could be anything at the end here. So hydrogen peroxide is the simplest peroxide, but it really could be any carbon chain on either side. And so that's just abbreviated by ROOR. Tells you have this peroxide, and that forces the addition to be anti-Markovnikov. The mechanism involves radicals, which we haven't discussed yet, and which we will discuss at length, and we will go through the mechanism for this at length in chapter 11. For now, what you have to know is that if you add peroxides to hydrohalogenation, it will give you the anti-Markovnikov product. Remember, in the Markovnikov product, hydrogen goes to the less substituted carbon. In anti-Markovnikov, hydrogen goes to the more substituted carbon. So using these two things, elimination and addition, and controlling where the double bond forms and where the leaving group is added, we can move leaving groups and double bonds across a molecule. Okay, let's take these ideas and apply it to this problem here. Now, do you see how ultimately we want to move this leaving group somehow to the right of the molecule? So as we do these reactions, we want to move things to the right. Now, when you look at the starting material and you compare it with the product, one thing you might notice is the starting material has a bromine here and the product does not. Now, when you're doing these syntheses, you always want to think in terms of big categories before you think of specific reactions. So what big category of reaction would have something there and get rid of it? And hopefully you're saying elimination. Now, in an elimination reaction, you could form the double bond either to the left or to the right. We want to form the double bond to the right. We want to move the reactive part of the molecule all the way to the right so that we can add a bromine on the right. Now, this is the Zaitsev product, right? The other possibility was if we had created the double bond on the left. This is mono-substituted. This is tri-substituted. The more substituted product is the Zaitsev product. We want this product. We want the double bond to go to the right, because that's where we want to move the leaving group. So we want the Zaitsev product. And the way you get the Zaitsev product as your major product is if you use a skinny base. A skinny base like sodium hydroxide. You could also use sodium methoxide or sodium ethoxide. Any of those would work for that skinny base. So that accomplishes that transformation. So it does something, but it's definitely not the product we want. Now, as we look at this molecule, there should be something standing out to you about this molecule. How would this molecule react? Hopefully, after studying this whole chapter, that double bond really stands out to you, and you think, oh, with double bonds, you use that as extramolecular glue to stick things onto a carbon chain. And so the type of reaction we're going to do is an addition reaction. You could see how I'm thinking very broadly. I'm not trying to figure out the specific reagents immediately that I'm going to use. I'm thinking in terms of big categories and then narrowing things down. So I'm going to do an addition reaction. You can see we're doing alternating elimination and addition reactions. What do I want to add? Well, when I look at these two carbons in the product, nothing is on them. So anything I add, I want to be able to get rid of it. In other words, I want to add a leaving group. And I want to add only one leaving group because I want to keep moving the leaving group over to the right of the molecule. And that's why we do hydrohalogenation. Now, it doesn't matter which halogen you use. I'm going to use bromine. You could just as easily use HCl if you want to. Now, in this case, you want the halogen to add on the right side of this double bond. You want the reactive part of the molecule to keep moving right. So you want the halogen to add there and the hydrogen to add here. Right? If it happened the other way around, you would just be back at your original molecule. So you want the halogen to add on that more substituted position. Right? So this is where you want this to happen. So you look at how do you control and make sure that the halogen adds on that specific position? Well, if you classify those two carbons, you can see that the carbon on the left is secondary and the carbon on the right is tertiary. You want the hydrogen to go to the less substituted carbon. And that is Markovnikov addition. So you want to do Markovnikov addition, so you just add HX. You don't add the peroxide. So just HBr, and that's what we get. Now I'm going to erase that hydrogen here because it's still there, it's just implied, and I want to focus on the reactive part of the molecule, which now is the bromine. Now, that molecule that we have is not the final molecule that we want. The reactive part of the molecule, though, is closer than it was originally. We've moved the halogen. We just want to move it one more time. So when I look at this carbon in this molecule and I look at the same carbon in the product, there is no bromine on it. So what big category of reaction does that suggest? It suggests elimination. If you have the bromine there to start with, but you don't have it there to end with, then you have to have eliminated it. So we're going to do an elimination. Now when you do an elimination, you could form the double bond in two different directions. We want to form the double bond to the right. We want to keep pushing the reactive part of the molecule to the right until we can add the bromine where we want it. So the two possible products you could form are forming the double bond where we want it to the right, or forming the double bond where we don't want it to the left. You could also form the double bond going up. Technically, if the double bond is going up, then it's the same thing as this here. It's as if you have flipped this molecule around. If you flip it like a pancake, then it would be as if the double bond were going up. So those are really your only two possible products there. Notice the product we want at the bottom is di-substituted. The product we don't want is tri-substituted. We want the less substituted product. That's the Hofmann product. We want the less substituted Hofmann product. So how do you control the product? How do you control an elimination reaction to get a Hofmann product? You use a bulky base. A bulky base like potassium terbutoxide gives you that Hofmann product as your major product in an elimination reaction. So you can use that bulky base here, potassium terbutoxide, and that would give you that double bond where you want it. Now we're almost home free. We have the reactive part of the molecule at the far right. We just don't have the bromine there. We have to add that bromine. Not only do we have to add a bromine, but we also have to add a hydrogen. Right now, there's no hydrogen on that carbon. There is a hydrogen on that carbon to end up with. We're going to do HBr. The question is, though, is this Markovnikov addition or anti-Markovnikov addition? So you can see we have to add things, so we're doing an addition reaction. Is it going to be Markovnikov or anti-Markovnikov? Well, we had a hydrogen add on a tertiary carbon. The bromine added on a primary carbon. So the hydrogen added to the more substituted position. To make a hydrogen add to the more substituted position, that's anti-Markovnikov. So if you want to do the anti-Markovnikov addition, you have to add peroxides. It changes the mechanism. So you would add peroxides. You could use a generic peroxide like I'm using here, ROOR, or if you want, you can use hydrogen peroxide, H2O2, whatever you want. But that makes sure that you get that anti-Markovnikov addition. And you've arrived at your product. So notice a couple patterns here. This is alternating elimination and addition reactions. First you do elimination, then addition, then elimination, then addition. You control where the reactive part of the molecule goes by using skinny or bulky bases in the case of elimination reactions, and by using peroxides or not in the case of addition reactions. For elimination, you're thinking about the Zaitsev or the Hoffman product, and for addition, you're thinking about whether you want Markovnikov or anti-Markovnikov addition. Notice all of the addition reactions were hydrohalogenation, and you knew to do elimination because you had a leaving group. If you have a leaving group, notice immediately after that you get elimination. On the other hand, if you have a pi bond, immediately after that, you do addition. So hopefully this gives you some sense of how you would approach these multi-step syntheses. They're the types of problems where you have to get started before you see the whole solution. You use patterns to get a foothold, and you work with that foothold. You don't try to see the whole answer all at once. And as you're working with each foothold, think in terms of big categories first, and then narrow down the specific reactants you might have. All right, it'll take some practice, but as you'll see, these multi-step synthesis problems can be very exciting because you can make very big changes happen to molecules.